Hello guys, I'm back. I'm going to continue with a brand new chapter for organic chemistry where we are going to learn about carbonyl compounds. So let's have a look at the content of the lessons. So in this chapter we shall learn about nomenclature of the carbonyl compounds, physical properties of the carbonyl compounds, chemical properties of the carbonyl compound, and carbohydrate as the carbonyl compounds. Okay, so with that organization, let's have a look at the content of the lessons. Carbonyl compound has a functioning group as C double bond O, which can be classified generally as the functioning group of aldehyde and ketones. So the carbonyl group of an aldehyde is flanked by a hydrogen atoms, so you should have a CH double bond O in here, while the carbonyl group of a ketone is flanked by in between two carbons, so you should have two alkyls surrounding the carbon. So aldehydes and ketones are neutral molecules and are actually responsible for many flavors and odors that are widely recognized. For example, you can have vanillin, cinnamon flavor, spearmint flavor, and almond flavor. So all of them comes from a carbonyl compounds. So let's have a look at the nomenclature of the ionic compounds. So to name aldehydes, so these are the four steps of how we name them. So find the longest carbon with chain containing CHO in it and name that accordingly. So aldehyde we'll name with the name Al. Then name the substituent in the parent chain, two or more substituents arranged according to alphabetical order, and based on the number of similar substituents, two similar di, three similar tri, and give the position of the number. So CHO should always be the first carbon. So if you have 1C, you have methanol. If you have 2C, we have ethanol. 3C propanol, 4C butanol, 5C pentanol, and if you have a benzene ring with a CHO here, we call it as a benzaldehyde. So this is how we name for aldehyde. So a few examples that you can see in here is if you have find longest carbon in here, so altogether longest carbon is 6 carbon. You have a methyl, you have an ethyl, so which is located at the 2, 3, and 4. So you have 4 ethyl, 2, 3 dimethyl hexanol. So in here, longest carbon in here is 6 carbon, 7 carbon. So you have 3 chloro, 4 ethyl, 2 methyl, 2 heptanol, since you have a double bond in between here. And if you here, this one is 2 hydroxy, 4, 5 dimethyl hexanol, and finally you have these 2 bromo, 4 ethyl, 2, 3 dimethyl hexanol. So you can get into the details on your own later. Yeah. Okay, so as for ketone, it is more or less the same. Find the longest carbon chain with a C double bond O in it and name accordingly. So ketone, we have the naming of the word on. So name the substituent in the parent chain if there are 2 or more substituents arranged in alphabetical order. So based on the number of substituents, 2 similar substitute dies, 3 similar substitute tri, and finally if give the number of the position of the substituent in the parent chains. Yeah. So since a ketone is in between 2 carbons, so minimum number of carbon that you should have for a ketone is 3C. So therefore 3C is called as propanone, 4C is called as butanone. However, starting from 5C onwards, you should name the position of C double bond O. For example, if you have C in here, you can see that this is how we name as a pentan 2-ons. Now, why is it that in propanone and butanone we don't have numbering? Because regardless what, it will definitely be the second carbon in here. So that is why we don't give numberings to propanone and butanone, because there will be definitely the smallest carbon in it, which is carbon number 2. And then you have a hexane 3-ons, so it indicates that the C double bond O is in the 3rd carbon. And then you have a cyclohexanones, and you have a phenylethanone. So this phenylethanone sometimes is also known as acetophenones. Okay, so way of examples of it. So here I have for you a few examples. So in here the longest carbon here is 7C. So you have a heptan 3-on. Okay, so you have a methyl, so 4 ethyl, 2 methyl heptan 3-on. In here the longest carbon is also here. So similarly, you have 7 carbon, so 5 ethyl, 2 hydroxy, 4 methyl heptan 3-ons, and then 2 3 dimethyl heptan 4-ons, and finally you have the last one in here, 2 bromo 4 ethyl, 1 hydroxy, 2 methyl hexane 3-ons. So this is basically of how you name all these ketones accordingly. So I'll leave it to you to understand on how to name all these ketones on your own. Okay, so that is all for the nomenclature. As for the isomerisms of the carbonyl compounds, you have to at least know how to write the formula for 4C and 5C. So 4C in here we have butanol, which is the most basic, and we have butanone, which is also another one, and isomers of aldehyde can also become 2-methylpropanol. And then if you have a C5H10O, so you have pentanol, you have pentan-2-one, pentan-3-one. So derivations of the aldehyde will give a 2-methylbutanol, 3-methylbutanol. Derivations of further aldehyde will give you 2,2-dimethylpropanol. And as for ketone, you have 2-methyl, 3-methylbutanone. Okay, so in here among them, this is optical active, so you should be able to draw the optical active isomers, which is looking like that. Okay, so this is the isomerisms inside the carbonyl compounds. And then as for the physical properties of carbonyl compounds, so for aldehyde and ketones, they are a little bit specials. They have relatively not a an average boiling point, not considered very low. They have an average boiling point, and small number of the aldehyde compounds are actually soluble in water. As the number of carbon increase, they become more and more insoluble in water due to the hydrophilic properties increase. So that is why you see that they are becoming less and less soluble in water. So later we'll explain that part. So this is a little bit physical properties of ketone. Only propanol and butanol are soluble in water, but when going down to the homologous series, they become more and more insoluble in water. Okay, so when going down the homologous series, the boiling point of aldehyde and ketone increase. This is due to as the molecular mass increase, the weight van der Waals forces that hold in between the molecule increase. As a result, more heat is required to break these forces. Yeah. Okay, so boiling point of aldehyde and ketone has a relatively higher boiling point compared to alkane and alkene. So if we were to compare in between, let's say butane to fluoropropane, aldehyde, propanol, propanones, and then these alcohols. Okay, so this butane and fluoropropane is considered as a non-polar molecule, so they are held by temporary dipole induced dipole, whereas these aldehyde and ketones, they bear a partial positive, partial negative. Okay, so the partial positive, partial negative there actually allows them to have permanent dipole, and because of that, so you have a higher boiling point. And the alcohols are held by hydrogen bonds, which are actually stronger than permanent dipole, so which makes alcohols the highest boiling point among all of them. Okay, so this is a little bit about the boiling points of the aldehyde and ketones compared to other functioning groups. As we described just now, we say that small number of the aldehyde and ketones are soluble in water because they are able to form hydrogen bonds in water, as you can see in the diagrams in here. However, this solubility decrease when going down to homologous series because the hydrophilic properties of the alkyl molecule increase when going down to the group. Okay, then so immediately we go to the chemical properties. So this is a giant mind map that I can show to you on how to relate all the chemical reactions of the aldehyde and ketones. You can see here there are two ways to prepare them. So you can prepare them by the following methods. You can prepare them by using this alkene ozonolysis. You can also prepare them via these partial oxidations of the alcohol by using copper at 400 degrees Celsius. So this is how you prepare carbonyl compounds. As for the reactions, you have a few. So for examples, you have at first when it can be oxidized, it can be reduced. Okay, then aldehyde can further oxidize to become carboxylic acid. The reaction with 2,4-dinitrophenylhydrazine. This is with Greek blood reagent, which we discussed earlier. Aldehyde can react with Fehling and Tollen reagent. the reaction with hydrogen cyanide and sodium cyanide, followed by hydrolysis or reductions. So, and finally, propanol react with alkaline iodine solutions. So all of them we are going to have a look one by one in details in here. So let's have a look at the way of preparing carbonyl compounds. So as described just now, carbonyl compound can be prepared via ozonolysis of the alkene, ozone followed by DMS, or you can use alcohols to prepare them. So you can heat off copper at 400 degrees Celsius, or you use PCC in an organic solvent at room temperature. So this is generally the way of how we prepare aldehydes and ketones in laboratory. As for the chemical reactions of alcohols, let's have a look one by one. What are the chemical reactions? Starting from the reductions. So our reducing agents in here is if you use tetrahydroaluminate, so followed by acidic hydrolysis, you can eventually form back the alcohols, where if it is an aldehyde, you form back a primary alcohol, and then if it is ketones, then you form a secondary alcohols in here. Okay, so this is more or less of the reductions of the aldehyde and ketones. So you use reducing agents such as LiLH4 followed by acidic hydrolysis. Yeah. Okay, and then you also can have oxidations of aldehyde. So in here, only aldehydes are able to further oxidize to form carboxylic acid using a strong oxidizing agent such as acidified potassium manganate or acidified potassium dichromate. So these are the equations for the oxidation reactions. However, once you oxidize to become carboxylic acid cannot reduce back to become aldehydes. As for ketone does not further undergo oxidations except when ketones is in contained benzene ring. For example, acetophenones that we discussed just now, if you use a strong oxidizing agent such as acidified potassium manganate, you can eventually form a benzoic acid. So this is the only type of ketones that can undergo oxidations, while the rest cannot. And then we also have the third reaction, which is the additional reactions, as we discussed previously in the chapter 4 in the Grignard reagents. So we know that under the additions of different carbonyl compound, different classifications of alcohols can be used in here. So the mechanism take place in here is a nucleophilic additional reactions. Yeah. So as described in the mechanism, when methanol react with a Grignard reagent, it will form a primary alcohol. So Grignard reagents, the partial negative of the carbons attacking the partial positive of carbon, and you form an alkoxide, and acidic hydrolysis will form a primary alcohols. And then if you react with aldehydes other than methanol with Grignard reagent, so you're able to form a secondary alcohol. So I'm going to use a similar cyclohexane so that you can see the differences. So when it attacks the carbon and you form alkoxide followed by acidic hydrolysis, so you are forming a secondary alcohols in here. And finally, for a ketone, so if you react with ketone, a tertiary alcohol can be formed when Grignard reagent is react with it. So similarly, the partial negative of the Grignard reagent attack the partial positive of the carbon in here and form alkoxide, which eventually undergoes acidic hydrolysis to form a tertiary alcohols. Okay, so the mechanism of how all this works is almost the same. So hopefully you'll be able to understand all that. And then the fourth reactions in the carbonyl compound is the nitrilations of the carbonyl compounds. When now you are reacting cyanic acid HCN with sodium cyanide as the catalyst, you first form a hydroxynitrile. So hydroxynitrile is also known as the we call this reagent as what we call that. Hang on. There's another name for this compound form. The name of this compound form is called as a cyanohydrins. Okay, so you contain you contain an OH and a CN at the same time. So this carbon is described as the alpha carbon in here. So this is one of the way of how you prepare a hydroxyl compound with cyanide compounds at the same time. So you must reduce it to become you must make it become an aldehyde or ketones for the further reaction. So this type of reaction is also a type of nucleophilic additional reactions. Yeah. So the mechanisms goes like this, where the catalyst reacting with the partial positive of the carbon, so electron transfer in here, and the hydrogens attack the alkoxide to form the hydroxyl. So you form cyanohydrins. and the Cn minus back as the catalyst in the initials. Okay, so these are more or less the mechanisms. And as we know that once you form a nitrile, there will be only two ending. It can be reduced to become an amine, or it can undergo acidic hydrolysis to become carboxylic acid. So now note that if you want to form a compound with OH and NH2 to appear at the same time, this is the only reagent that we can use to do that. Or if you want to have a compound containing OH and COH bonded to the same C, also similarly, this is the only compound that can form OH and COH at the same time. So please bear this in mind in here. Okay, so this is for reactions with the hydroxyl nitrile. And then the mechanisms, this is for ketones, so it's more or less the same as we described just now. And as you can observe, it is also the same if you react with a lithium, you form reduce to form NH2, and acidic hydrolysis will form a COH. Okay, so that is for the reactions of the nucleophilic additional reactions of a cyanic acid inside a carbonyl compounds. Okay, so hope that you remember. Now the next reaction in here is the reaction with 2,4-dinitrophenylhydrazine. This 2,4-dinitrophenylhydrazine also has a name, we call it as a Brady reagent. Okay, so this is how 2,4-dinitrophenylhydrazine looks like. So if possible, try to memorize them. Okay, so this type of reaction is a type of a condensation reactions, okay, where in here you form as an orange precipitate. So this works for both aldehyde and ketone, and it is a basic test to test the presence of the carbonyl compounds. So this is a very, very important reactions if you want to identify a carbonyl compound. So it works for both aldehyde and ketones in here. Okay, so this is the examples by using ketone. So you form hydrazone, we call this, and which is the orange precipitate. Yeah, so this reaction is also a type of hydrolysis. Okay, so that is all for the chemical properties of the carbonyl compounds. And then we are also going to have the side reactions of a chemical test for aldehyde and ketone. The first test we are going to see in here is Iodoform test. For Iodoform, we are going to use alkaline iodine solutions. Now for aldehyde, okay, aldehyde, it only works for ethanol, okay, because it contains a methyl carbonyls group. So this is a methyl carbonyl group. So what we observe as yellow crystal or yellow precipitate is formed according to these equations. As for ketone, anything with 2 on, okay, anything with 2 on, okay, it will give a positive test because they have a methyl carbonyl group. Okay, so you observe a yellow crystal. So you can have propanol, butanol, pentan 2 on, hexane 2 on, even phenylhydrazone. All of them will acetophenone, all of them will works well for this Iodoform test because all of them contain a methyl carbonyls group. So this is the examples of the equation for the reaction. So this CHI3 is the one that is formed as a yellow precipitate Iodoform. Second reaction is the Fehling solution. So Fehling solution is actually a solution containing copper complex. So in alkaline solution, so it will works only for aldehyde except for benzaldehyde. So benzaldehyde will not works for Fehling. The reactions in here where it is aldehyde, for example ethanol in here, when you react with copper, so it will turn from blue solutions to become a red brick precipitate. So this red brick precipitate is due to the formation of Cu2O, and at the same time you form a carboxylate ion. Now if you study properly in here, from the carbonyl compounds to become a carboxylate, this is an oxidation reaction, and from copper 2+ to become Cu2O, this is actually a reduction reaction. So this reaction is basically a redox reactions where ethanol in here act as a reducing agent. Okay, so similar like to Tollen reagent. So Tollen reagent is a solution containing diamine silver complex AgNH32. So it will only works for aldehyde, okay, and where you observe a silver mirror in here. So this similar to the case just now, it is also a reduction reactions where at the end you form a carboxylate ions, and silver in here is reduced to form the silver mirror that you see as the precipitate. So it will works for all carbonyl compounds in here. Yeah, okay, so this is the basic chemical test of the aldehyde and ketones. And last but not least, we're going to have a look a little bit about carbohydrates. So carbohydrates are defined as a polyhydroxyaldehyde and ketones that hydrolyze to yield polyhydroxyaldehyde and ketone. So exist primarily as hemiacetal or acetal form. A simple carbohydrate is called as a monosaccharide. So monosaccharide contain multiple chiral center, and Fischer projections are often used to indicate the configuration of each chirality. So glucose and fructose are two examples of simple sugar. So you can see in here, glucose is also known as an aldohexose because it contains an aldehyde as a functioning group. Fructose in here is a ketohexose because it contains a ketone as the functioning group. Okay, so due to the presence of the aldehyde, so glucose in here can oxidize to form carboxyl group, so therefore can act as a reducing sugar. So this is the equation when you react with a Fehling solution, where this aldehyde eventually be oxidized to become this carboxyl compound, carboxylate ions in here. Okay, so similarly you see a Brady precipitate for glucose, yeah. And then one of the best things, one of the side reactions about this monosaccharide is when you join together by using glycosidic link, eventually they can form disaccharide. And if three molecules, you can, most of the most common disaccharides are sucrose, maltose, and lactose. And since forward reaction is a condensation, okay, and therefore all disaccharide can be hydrolyzed to form back the monosaccharide in here. Okay, so this is how the reactions works lah. Okay, so with this I finish chapter 6. So hope that you enjoy the video, and I'll see you in the next chapter. Thank you.